Hi, my name is Erica Carlson. I'm a theoretical physicist at the Purdue Quantum Science and Engineering Institute. And it's a great pleasure to be interviewing today Doug Natelson. Doug is the chair of the Physics and Astronomy Department at Rice University. He's also a member of the Rice Center for Quantum Materials. And Doug does a blog on called Nanoscale Views. I'll put a link to that in the description, so be sure and check out Doug's blog. And Doug's also written a book recently on nanostructures and nanotechnology. I'll also put a link to that in the description in case you want to check out either his blog or his book. Welcome, Doug. This is Quantum Connections, where we like to have conversations with quantum scientists and engineers. And so the first thing I'd like to ask you today is, why are so many researchers excited about quantum science and quantum engineering right now?
Well, I think the trick is we now, as a field, we know enough and we have enough techniques and skills that we can actually do experiments and projects that before were kind of the realm of thought experiments. So, people have known about quantum mechanics since the 1920s and before, and we've long thought, boy, wouldn't it be great? Physicists often talk about, oh, wouldn't it be great if we could reach in and do this and set up this system, this idealized system. And there's this long history of quantum thought experiments, Schrodinger's cat, and so on and so forth. And now we actually have comparatively well-controlled systems where we can really apply the ideas that we've been thinking about for a long time and actually do fun and new things. And on the materials front, I think the kind of over the 20th century and into the 21st century, it's been the story of really understanding where the properties of materials really come from and learning to exert some degree of control and engineering of these things. And I think particularly over the last, say, 25 years, people have really gotten to the point where they can do some pretty amazing things in terms of controlling material structure and understanding and probing materials at a level that they couldn't do before. So we really have a much deeper understanding than we used to. And that's kind of the way things tend to work. Science is to some extent figuring out the rules that run the universe. And then engineering is taking your knowledge of those rules and applying it to solve some problem you care about or to test some ideas that you want to test.
I'm curious, and I think some of our listeners would be curious, what originally got you interested in doing science?
That's a really good question. So my mom was an English teacher and my dad's a retired engineer. I've always been kind of a gadget guy. That probably is why I'm more interested in doing experimental work, though these days that involves my students doing experimental work. But I don't know. I've always kind of been fascinated with how the universe works. At an early age, I kind of got hooked on watching things like Nova and Cosmos on TV, and that really struck a spark. And there's no question that reading science fiction has also had some influence, and watching science fiction movies has had some influence on me. I've been kind of a science person from an early time, and when I was an undergrad, I really was fence sitting. I was trying to decide whether I wanted to do engineering or whether I wanted to do more researchy science stuff. And so I did what you ought to do in a situation like that, and at least I was fortunate enough to be able to do. I kind of tried both. So my actual undergrad degree is in mechanical engineering, and I did some engineering projects. I did some an engineering summer job, and decided, what I actually really like is more the figuring out the rules part than the design side. So that's kind of how I ended up going in a career more in the science direction.
I know you've got a lot of things going on in your research lab, but is there something in particular that you'd like to tell us about today? Maybe there's something you're most excited about in your research program right now?
Sure. Well, as you said, we've got several different things going on. Something we did relatively recently that I think is pretty cool is we did some measurements of noise. So usually you think of noise as this thing that you want to avoid. It's this thing that interferes with your ability to listen to music, say, or your ability to do measurements. Noise is usually a bad thing. But actually noise can tell you a lot. So let me give you an example. If you're driving in your car and it's raining, right? you can figure out how big the raindrops are that are hitting your car by the noise they make. So you can have the same amount of water hitting your car, but it'll sound very different if it's hitting your car as a mist versus if it's hitting your car as a few enormous raindrops widely separated in time, right? So in the big raindrop case, the fluctuations from moment to moment in the water flow are much larger than in the fine mist case. So what we did was a measurement using some exquisite structures grown by our collaborators at Brookhaven National Lab. There are these materials, the high temperature superconductors, that have been mysterious since their discovery 35 years ago. People still don't understand why they work and why. So superconductivity is this special state where electricity can flow without resistance. So if we had lots of room temperature superconductors, we could really change the world in many interesting ways for technology. So people are still trying to figure out how these high temperature superconductors work. And in ordinary superconductors, a key to superconductivity is that the electrons, the little charge carriers, they pair up. And in something like an ordinary superconductor like lead or mercury at low enough temperatures, these electrons, they pair up, and as soon as they pair up, they form this state that allows superconductivity. And so in these funny copper oxide ceramics, people still don't quite understand how this works. And so we did a noise measurement where you take a layer of this copper oxide superconductor and another layer of the superconductor, and you let current flow, you let it quantum mechanically tunnel from one side to the other through an intervening layer of a special kind of insulator, in this case something called a Mott insulator. And instead of just measuring the current as a function of the voltage you're pushing across this thing, we measure the fluctuations in the current. So we're measuring the noise. And there is an expectation, there is a formula about what you should see if the charges are coming across one electron at a time. And what we actually see is greater noise than that. So it's as if the droplets are bigger. So what it seems like...
And those high temperature superconductors, can you just give us a sense real quick of what that temperature scale is for the high temperatures?
Okay, so high temperature can be as high as 100 Kelvin, which of course is still like minus 170 Celsius. So it's still pretty cold. But
so pretty cold to humans, but we call it high because
something like lead superconducts at 7 Kelvin. Okay, so they're much warmer than the traditional, originally discovered superconductors that were first found 110 years ago. So what we find is that the noise seems to indicate that even in a situation where the superconductivity isn't there yet, the electrons are already pairing up. There seems to be some amount of electrons going through two at a time. And so that's one thing that we thought was interesting. Other people had seen hints of that. The other thing that we thought was interesting was that you can, by dialing up your battery, by dialing up your voltage, you can tune the energy you're looking at. And we found that there's hints that there's still pairing going on even at energies that are big compared to what you think of as this energy scale for superconductivity. So that suggests, it doesn't prove, but it suggests that in these copper oxides, the thing that kills superconductivity, when superconductivity dies, when you warm this material up, it's not that the pairs fall apart. The pairs might still be there. The issue is more that the pairs can't talk to each other in a coherent way and form this nice coherent state. So if you could find a way to make all the pairs dance together and synchronize them up, then maybe you could get superconductivity to happen at considerably higher temperatures. So there's a lot more yet to do, and we've got kind of a list of experiments that we want to get to once us and our collaborators are out of the COVID-related research slowdown. But it's been a lot of fun to play with these materials and to do these kinds of measurements. It's really, this is the fun part of science, right? You have this idea that maybe it would be interesting to look and see whether you can detect pairing, or there's even more exotic models that suggested that you should see almost no noise when you do this experiment. And so it's fun to actually set this up in the lab with your students and do the test and see what you actually see. That's the whole difference. That's the whole difference between doing research and kind of the labs people often do in school, where like everyone kind of knows what you're supposed to get, And the fun part of the research is you don't know what you're going to get.
Thank you so much for talking with us today on Quantum Coffee House and telling us a little bit about your interest in science and in all things quantum and in the work going on in your lab. Thanks a lot, Doug.
Thank you. Take care.